The topic we're about to cover, work and energy, makes use of the so-called scalar or dot product. So in case you haven't covered this yet in your math class, I thought it would be good for us to talk about it here. This is a way of taking two vectors, multiplying them together, and getting a scalar out of it. So suppose we have one vector that we can call A, and we have another vector that we can call B, and there's some angle in between them I'll call phi. The dot product is defined this way. If you take vector A and multiply it by the dot product into vector B, what you get is a scalar that equals the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. So you can see the geometrical interpretation here. The dot product shows you how far one vector projects itself onto another vector. Let me draw the component b cosine of phi. It's this orange component right here. So that's b cosine of phi. So when we take the dot product, a dot b, what we're doing is we're taking the length of the first vector and we're multiplying it by the component of the second one in the direction of the first. So that's what the dot product gives us. You multiply two vectors together and you get a scalar out of it. That scalar shows you the extent to which one vector projects itself in the same direction as the other one. The dot product can be positive, it can be 0, or it can be negative. It is positive if the angle phi is acute, if the angle phi is less than 90 degrees. That is, if the two vectors have components in the same direction as each other. The dot product is 0 if the two vectors are perpendicular, if the angle phi is 90 degrees. So you can see that here. If this is vector A and this is vector B and they're perpendicular, then there's no projection of the second vector along the first one, and that dot product's going to be 0. And the dot product can be negative if one vector projects itself backwards along the other one. If the angle between the two vectors is greater than 90 degrees. That would be a case like this. If vector A looks like this, and vector B was over here, so that the orange component, B in the direction of A, is over this way, where this is the angle phi, then that dot product is going to be negative, because B projects itself backwards opposite the direction of A. So that's how we calculate the dot product. Here's the basic definition of it. A dot B is magnitude of the first vector times magnitude of the second times cosine of the angle between them. The dot product can be positive if the angle is acute. It can be 0 if the vectors are perpendicular, and it can be negative if they generally point in opposite directions. There's one other useful way to write the dot product. When you want to calculate the dot product, you can use this definition if you know the magnitudes of the two vectors and the angle between them. But sometimes you don't know that. Sometimes what you know instead are the components of the vector. Let me erase this box and some of this other stuff, and I'll show you what I'm talking about. So let me get rid of this. Suppose, instead of knowing what the lengths of these two vectors and the angle between them is, suppose someone instead told us that, for instance, the vector A was 3i hat minus 2j hat plus 4k hat, and the vector B was I hat minus 2j hat minus 3k hat. And they asked us to calculate the dot product. Well, we could certainly find the magnitudes to get A and B. Square the components, add them up, and take the square root. So we could find A and we could find B, but I don't know the angle between these two vectors. I don't know the angle between this vector and this vector. So I'm stuck. I can't evaluate this thing. The way to get around that is to come up with another way to calculate the dot product when you know not the magnitudes and angles, but when you know the components. So let's suppose that we write this in a general way. The vector A is ax I hat plus ay j hat plus az k hat, and the vector B was bx I hat plus by j hat plus bz k hat. And now, when we want to calculate A dot B, what we're going to get is a big distributive law problem. We're going to have this. Let me write it really quickly here. Okay, so I'm going to have 9 terms in the end. I'll have this term dotted into those 3, plus this dotted into those 3, plus this dotted into those 3. I'm going to write some of these terms. The first one is going to be this term dotted into this. So I'll have ax bx I hat dot I hat. The second one's going to be this dotted into this. ax by I hat dot j hat. And then I'll have this dotted into this. Okay, then we'll have 6 more. Let me go ahead and write them. ay bx j hat dot I hat plus ay by j hat dot j hat plus ay bz j hat dot k hat plus az bx k hat dot I hat plus az by k hat dot j hat plus az bz k hat dot k hat. All right, there they are, all 9 of them. And now our problem comes down to figuring out what these things are. What is I hat dot I hat? What is I hat dot j hat? What is I hat dot k hat? And what are all the rest of them? Let's figure that out. We'll do that up here. We'll get a little bit of room. And let's draw ourselves a coordinate system. Here is a XYZ coordinate system. So in 3 dimensions, we have X, Y, and Z. Now I hat is a unit vector, has a length of 1 in the X direction. So I hat looks like this. J hat is a unit vector, length of 1, in the Y direction. So it looks like this. And K hat is a unit vector, length of 1, in the Z direction. So it looks like this. Okay? So now let's go through and see if we can work out what all of these dot products are. I hat dot I hat. If I want to calculate the dot product, all I can do so far is use this definition here. It tells me the dot product of 2 vectors, I hat and I hat in this case, is the magnitude of the first times the magnitude of the second times cosine of the angle between them. The first vector is I hat. It has a length of 1, so we have 1. The second vector is I hat, length of 1, and the angle between the x-axis, where I hat points, and the x-axis, where I hat points, is 0. Cosine of 0 is 1. So this whole thing here, I hat dot I hat, equals 1. So that's good. The next one says I hat dot j hat. Okay, same definition. Length of the first vector is 1. Length of the second vector is 1. Cosine of the angle between them. I hat is perpendicular to j hat. So cosine of 90 degrees is going to give us 0. And this is 0. I hat dot k hat. Same business. 1, 1, cosine of 90 degrees, because the x-axis is perpendicular to the z-axis, and that's 0. And you can see the pattern now. J hat dot I hat is going to give us 0 because the y-axis is perpendicular to the x-axis, 0. But here's a j hat dot j hat. That's going to give us 1. Here's a j dot k, 0 because y is perpendicular to z. 0 because z is perpendicular to x, 0 because z is perpendicular to y, and 1. What survives here are the diagonal terms from these 9 original terms. So look at which ones survive. ax bx plus ay by plus az bz. So the other way to calculate the dot product, if you know components, is to write it like this. ax bx plus ay by plus az bz. So that's the second way to calculate the dot product if you know components. We can do as an example. Let's erase this here. We can calculate the dot product of this vector A into this vector B. Let's do it right here. So A dot B, what is it going to equal? It's AX times BX, 3 times 1, plus AY times BY, minus 2 times minus 2 is 4, plus AZ times BZ, that's minus 12. And that turns out to be minus 5. 7 minus 12 is minus 5. So this dot product A dot B is minus 5. So by the way, this is a good way to work out the angle between two vectors. If somebody asks you, what is the angle between this vector and this vector, the way you could find it is to calculate the dot product. You could calculate it this way. In this case, you would get minus 5. If you know the length of vector A and the length of vector B, you can take that product, move it over here, take the inverse cosine, and find the angle between any two vectors that you want. All right, so that's the dot product. An important thing about it is that it can be positive when the two vectors generally point in the same way. It can be 0 when they're perpendicular, and it can be negative when they generally point in opposite directions, or when they have components pointing in opposite directions. This will come up in the next talk when we start to study work and energy.